This is here are the three possible trees that I showed you. We all agree that those are three possible trees for 4 species. And the idea is we want to basically measure how well the alignment fits each of those 3 trees. And so this is this is the only time I really showed you a special effect. I've been using them sparingly, but I couldn't help myself. But what I've done here is, you notice each one of the columns is color-coded? What I've done is I plotted on the trees where you would infer character changes on each. So for instance, look at the last column, and notice I have that kind of gold bar in the center branch there. That is the inferred position for a single change for that sequence. Note that for that position you have G assigned to 2 and 4. These 2 species have the nucleotide G, and these 2 species have the nucleotide A. So what that gold bar represents is the change from A to G or G to A. Okay? What we've done here is we plotted where the changes have occurred on the tree in such a way that we minimize the number of changes. This method is called the parsimony method. It's the one you'll be introduced to here, but also in labs. It's the so-called parsimony method. And the idea is that you can sum up the number of possible changes for each of the 5 columns in that alignment. So the very first column requires 0 changes on this tree. The second position requires 0 changes on this tree. The third column requires 1 change, as does the fourth. And the fifth column of that alignment on this tree requires 2 changes. So the total number of changes, you sum them up is 4. Here's the same exercise for the second tree, and here is the same exercise for the third tree. Okay? So the parsimony method works in a similar way to other methods in that it assigns a score to each possible tree. Right? So you can think about if you have 10 species, every one of the 2,027,025 possible trees gets a score. And the best tree is the tree that minimizes the number of changes. So our best estimate of phylogeny would be this unrooted tree, right, for this made-up example. But the real problem faced by the biologist, at least a person like me, is you need to write a computer program that somehow searches through all the possible trees and tries to find the tree or trees that minimizes the number of changes. Okay, and there's some very good computer programs out there that do just this method. I'll show you one in a bit. So let's think about this, though. So here is one of those 3 possible trees that was the best tree. And what I'm going to do is I'm going to put the 4th column, the nucleotides for the 4th column to the tips. Right? So there's a large number of different ways in which one can map the characters onto the tree in such a way that the history of change along the branches is consistent with the observations at the tip. So here's an example of one that requires 7 changes. Right? You all agree? So that's to say you go from a G, and this is to say you have a change from G to T, and then T to C, and C to G to G. Then along this branch you have T, T to C, C to G, G to A, and then into the A, the thing you observe. Right? There's a large number of ways we can actually map these characters onto the tree in such a way that they be consistent with the observations at the tip, the observations we actually make. In fact, there's an infinite number of them, so I should have no problem coming up with some other examples. Here's another one. Right? I could spend the rest of our year going through examples on this one tree of different histories that could explain it. Here's another one that requires 5. The parsimony method says, even though we recognize there's a large number of possible ways we can map the characters on the tree, parsimony method says we only consider the histories of change that require the fewest. So if you go through, there's only the only type of change or history that requires 1 change is the only one that the parsimony method cares about. Okay? Is that clear? So I'm just trying to give you some idea that we have a number of possible trees, and then for each tree we're going to be assigning a score. Parsimony method would say we're going to choose the tree that minimizes the number of changes required on the tree. And you just have to recognize that the parsimony method is making this decision that the character histories that matter are the ones that require the fewest number of changes. It's ignoring all the different histories that require a larger number of changes. All right, so I'm going to give you obviously a demo now. What I'm going to do is fire up a computer program that actually does this. I'm going to change to documents, Nexus files. So I'm going to use a computer program called POP. This is all from the command line, so don't get freaked out. This is a computer program called POP. It was written by a fellow who's now at Duke by the name of David Swafford. And for a very long time, this was probably the most widely used computer program for inferring trees. Okay? What I'm going to do is read in an alignment of DNA sequences. I might as well show it to you, I suppose. I'm going to go to my documents folder. This is probably not the best thing to be doing in front of hundreds of people. But here is an alignment that I'm going to show you. Open up Wikipedia. Here is a real-life, genuine, not fake alignment. Right? Going to, there it is. Human, chimp, gorilla, orangutan, chimpanzee, and human, right? So 5 sequences. Like I said, I could choose another one. But there's an alignment. This goes back actually ages. It's quite an old alignment. It goes back to the 80s, right? Before you guys were probably born. So that is the alignment we're going to look at. Maybe it's a better one we could look at. I think there is. Maybe this one would be better. This one's better. Let's look at this one instead. Let's forget that one. Here's another real-life, genuine alignment, not made up at all. So here is this is the actual paper. This one goes back to 82 by Hayasaka et al. 1988. Molecular Phylogeny and Evolution of Primate Mitochondrial DNA. Published in Molecular Biology and Evolution, very good journal. But here are the species that they looked at. One of these species, the lemur, they want to consider as the outgroup. Okay? So let's go ahead and let's read that alignment in. So I'm going to say execute bm.nex. Is that the file I wanted? Yes. So now I have read this file in. Notice that it says number of in-group taxa 11. 1 taxon transferred to the outgroup. Which species was transferred to the outgroup? Let's see. The lemur is the outgroup species. Great. All right. So now what I'm going to do is, how many species do we have? We have 12 species. That means there's going to be several billion possible trees, right, that we have to search through. The computer program is going to use a method that's quite fast to find trees. They just found it. They found 2 trees that were equally good. As I say, both of these trees out of the couple billion possible trees had an equal parsimony length, required equal number of changes, and the number of changes required was 1,153. The idea here is that of all the billions of possible trees, those 2 trees require the fewest number of changes for that alignment of DNA sequences I showed you. And this is why I use computers too. First of all, you try to map a couple thousand characters onto a tree without making mistakes, right? It's unlikely to happen, and you do it much more slowly. Now let's look at those trees. Here is one of the 2 equally good trees. Notice that the tree is drawn in a rooted way. This is kind of ASCII art. It's really hard to actually do this. I've written a program that actually prints out trees using ASCII symbols, and it's not fun. But here's an example of an ASCII being the character's tree. It's rooted at the lemur. That is to say, in computer memory, the tree was unrooted, but then when it's displayed to you, it's rooted by where we said we wanted the outgroup. And let's just concentrate on the top part of this tree. Pan, that is the chimpanzee. Homo, that's us. Gorilla is, well, the gorilla. Pongo is the orangutan. Hylobates is the gibbon. Right? This is the tree that is the agreed upon one now. Since the 1980s, as more and more people sequence DNA, as the entire genomes of each of those 5 species has been sequenced, we are very convinced now that this is the right tree. But in the early 80s, there was actually some disagreement. In the late 80s as well, when this paper came out. And the reason is that even though this is one of the 2 equally parsimonious trees, look at the other one. This is the only place this tree differs from the other one is the one up here has humans and chimps as each other's closest relatives. Like I said, what we think is what really happened. Versus this one, which has the chimp and the gorilla as each other's closest relatives. See the difference? So for a long time in human evolution, there was this debate about exactly that part of the tree. Are chimps more closely related to humans, or are chimps more closely related to the gorilla? It's become resolved since in the last 20 years, but at the time when this paper was published, there was some debate. And here, the other point being that both of these trees require the same number of changes. So they're called equally parsimonious trees. The idea here is that the computer program isn't returning 1 result, but 2 results. Right? But this is this was on the fly. I did not actually even check this beforehand, but I kind of knew what would happen more or less. Right? This is an example of a phylogenetic analysis done live in front of you. If that excites you, probably doesn't. All right. So are there any questions? I mean, this field, you can spend actually teach an upper division course on phylogenetics, which I don't know how many of you actually want to take, but there's a lot of math and there's a lot of computer science involved in these types of problems and also statistics. But you get the basic idea. You have a universe of possible trees. The number of possibilities is defined before the problem. We assign each of those trees a score based on some observations you make, and then the computer science problem is to search through all those possible trees to find the best ones. Go ahead. You have questions? No, so that's another set of problems that you can address in a phylogenetic analysis, but you have to do them in what's called a more model-based method. They have to be methods that I would agree with more to do these things. But one thing you can do is you can assume the molecular clock, and a lot of people do that. And the basic idea, if you assume the molecular clock, is the following. If the molecular clock hypothesis is true, I talked about it when we talked about population genetics, and then I just kind of dropped it, but it comes into its own when people talk about comparing DNA sequences and trying to infer the time at which the speciation events occurred. So let me describe what's happening. The molecular clock hypothesis is that changes accumulate at a constant rate. That is to say, differences between species accumulate at a constant rate. That is the molecular clock statement. So if you have a molecular clock tree with species, say, human, chimp, and gorilla, if you know, well, this is I can take any example. Let's not take human, chimp, and gorilla. Let's make this A, B, and C. A, B, and C. The first thing is if you infer this tree under the clock assumption that all the changes along the branches are constant. If you know for a fact that this occurred 10 million years ago, this is called a calibration. You have to have some external evidence that would allow you to calibrate this tree. That is to say, allow you to point to at least one node, one speciation event on the tree and say, we really think this occurred 10 million years ago. The other thing is you have to know how much change occurred along each of these branches. So for instance, make this easy, 0.1, 0.1, this would have to be 0.2. These numbers are the lengths of the branches in terms of the expected number of changes per site, per column in the alignment. So this would mean that if you had 100, if your sequence was 100 nucleotides in length, then we expect 10 changes along this branch, 10 changes along this branch, 10 changes along this branch, and 20 changes along that branch. That's what the molecular clock is stating. So molecular clock allows you to get these numbers. The calibration says that you're absolutely certain of this time, but those two things together let you say, aha, if the molecular clock is true, then 0.1 changes equals 10 million years. So that would mean that this would have to be 20 million years. This is the inference. This is the type of analysis that's been done that allows us to make a statement of the following sort. Based on DNA sequence data, we think that humans and chimps diverged 5 to 7 million years ago. Right? It relies on there being some calibration within primates, not within apes, somewhere else on the tree, and a clock type of assumption in the analysis that allows us to make a statement like that. So that's why the molecular clock hypothesis that I introduced in population genetics, this is where it actually comes into play when you're comparing DNA sequences and you want to make inferences about when various speciation events occurred on the tree of life. Even if the fossil record isn't sufficient for you to actually pinpoint it, the genetic data might help you. Okay, you had a question too? So there's a couple biological justifications for it. There's a philosophical argument, which is why it's called the parsimony method, that if you have several different competing hypotheses that can explain some phenomenon, that you choose a simpler one. That's the philosophical argument. It's one that I can't frankly get too excited about personally, but there's some people that would slap my wrist for saying this to you guys. So hopefully they won't hear about it on the internet. But there's biological reasons for it too. So in general, if the rate at which substitutions accumulate, as I say, if the molecular clock is running slowly and the species are closely related to each other, then on average you will not have very many changes along the branches of the tree. So actually in that case, the parsimony assumption is not a bad one to make. That usually it's the case that the number of changes between them will be actually the parsimonious number. Not guaranteed, but that's why actually I prefer methods that let you spread your bets over all infinite number of character histories. There's ways of doing that mathematically, and those are the methods I prefer. But the point here is I'm not trying to push any particular method on you guys because I'm not telling you the methods. This is the parsimony method illustrates all the aspects of the phylogeny problem that I care about, that I care about you knowing. Are there other questions? Okay, so in the last bit here, maybe in the beginning of the next lecture, I want to show you some interesting results. Or at least what I guess the people are interested in themselves, of course. So where we fit in the tree of life is always of interest. But our last lecture will probably cover that. But this just gives you a table that I guess I'm talking about in lecture, but frankly I would not expect you to remember all these numbers. But just to give you an idea of the number of species in different groups. It gives you an idea of the scale of the problem that we're facing if we want to make a tree of life. I already told you that if you have 60 species in your analysis, you already have more possible trees than there are known atoms in the universe, or atoms in the known universe, however that's counted. Well, look, minimally we have 1.7 million counted up species, right? How many possible trees are there? So it's a number that has 10 raised to a large number of digits, right? Possibilities. And then we have estimates on what the low ball estimate and the high ball estimate is for the number of species on Earth. So that the tree of life is big. And that's just counting up the number of tips that we have, right? Most species that have ever been alive are now extinct, right? And this, there's the diversity, much of it is not diversity you can see with the naked eye. Most of it, in fact, is microbial. Here's an example of different types of bacteria. And one of the earliest results is actually how all species are related to one another on Earth, right? And so this is a phylogeny that you can sort of think of as the equivalent of those T-shirts you see with the galaxy, the Milky Way, and a little arrow that says you are here. This is the equivalent for phylogeny. I have to find out where are humans. Anybody see Homo sapiens on this? Oh, here it is. There we are, right? You are here, right? And what we have close to us, well, to give you an idea of the scale, that's corn, all right? But the idea here is that the tree of life is quite diverse. The parts that we typically think of as being quite different one from the other represent only small parts of the tree of life. And this is an early phylogeny that came out maybe 20 or more years ago that divided the tree of life into three main domains: eukarya, archaea, and the bacteria. Okay. And as an aside, how do you use the outgroup species for it? How do you use the outgroup method for the tree of life? What is the outgroup for life? Right. That's the type of problem phylogeneticists face. That's why I put this tree in an unrooted form. What are you going to root it to mud? I mean, it's not clear where you root it, right? How you root the tree. All right, so that's just an example of the big scale. Here's an example that I think at least, there's a good chance that many of you, at least at one stage in your life, like dinosaurs a lot, right? And here's some examples of dinosaurs. This is Tyrannosaurus rex. This is the skeleton you find in the Field Museum in Chicago. And then here's a picture, a drawing somebody made of a dromaeosaur in real life. Okay, I'm joking about that. It's just somebody's depiction of what a different type of dinosaur looked like. But note that a lot of these dinosaurs appear to have feathers. Actually, in some cases, these things that we know are dinosaurs that were not birds were running around and they had feathers. Right? And here's an example of a phylogeny of just the bird part of it. So what we have here is some things we call dinosaurs that had simple feathers. There's Archaeopteryx, complex feathers, and then the reduction in the number of tail vertebrae. here's where we see the appearance of a breastbone with a keel for attachment of muscles and so forth. So on the very right of this tree, which remember I can rotate this and not change the meaning at all, but for convenience I put the most modern birds on the right and the more basal, some people call primitive, that's another thing you try to avoid, birds on the left. Archaeopteryx is an example of a bird that was found in the Jurassic it's a mosaic. It has feathers, it clearly could fly, but it had a tail, it had teeth. Right? So when you think about a lot of phylogenies can be useful because they can actually give you information about the appearance of characteristics in a group that's quite different from others. You look at birds and they have all sorts of features that distinguish them from other species. They're close as well as the crocodiles. They have feathers, they have hollow bones, different metabolism, they don't have teeth, right? And there's a lot of things that distinguish birds from their closest living relatives. Well, these phylogenies can make sense of these characteristics. They didn't all appear at once. They appeared piecemeal over time. And in fact, feathers appears in many different dinosaurs that clearly could not have flown. So for whatever the reason was that feathers evolved, it wasn't for flight because you had things that were old, that are more basal on the phylogeny, that had feathers that clearly could not have flown. So the feathers were later exacted is what they called it. The purpose changed and they became the fodder for flight. I'm going to stop there and talk about a couple more examples of phylogenies in the next lecture.